All right, continuing on with class 6, this is sample problem 3.2. And as I said in sample problem 3.1, I'm going to solve it a little bit differently than in the book. In the book, they decided to, once again, continue with what equivalent moments are. Instead, we're going to go and do the reaction moments. Reaction moments being what we most often will try to find when trying to do one of these kinds of problems. And I'll point out the two different ways that we can approach this problem. And I'll continue and do that with sample problem 3.3 as well. So we start off by making a free body diagram, the all-important free body diagram. And let me give myself some room. There you go. Now down here, I'm actually going to do it a second time, so let me give myself some space there too. And okay, so in terms of, I should also, I should be consistent here. And here's X. Whoops, that was all terrible. X and Y. Here's the positive direction. Let's put down here too. X, Y. Here's the positive direction. All right, so the loads that I'm going to apply up above, I'm going to go ahead and break these down into X and Y directions, right? So I'll put it up here at the top. I'll go Fx is 800 times the cosine of 60. And so it ends up being, we could do this in our heads, 400 newtons. Fy is equal to 800 times the sine of 60, which is equal to 692.8 newtons. So applied right here, did I label it? Yes, I did. 400 newtons and 692.8 newtons. Then I put my reactions on here. And just from observation, I know that the reaction here in the y direction must be down. The reaction here in the x direction must be to the left. And now I need to have a moment reaction. Generally speaking, I choose as my default counterclockwise if I'm not sure. Now, sometimes it's obvious from the problem. And I'm going to go call this MB. So the reaction is called MB. It's a specific moment. But I'm also, when I take my summation of moments, I'll say summation of moments about B. What I mean up here when I write MB is that it's all the moments about B. But now, including one of them, that's a reaction. So as I'm trying to go march through this, let me take the x direction first. And I need to find the distances, right? So for the moment arm. So there's the line of action that's happening right there. So the distance that I would use is the perpendicular distance to this point, which ends up being this guy right here, which ends up being 1600, right? You can see that, you might look at the line of action and look that that's perpendicular. So that's not 1600, but 160 millimeters. And by the way, we don't really ever write Newton millimeters, right? Let's look for Newton meters, right? Is the typical units that we would use for torque or for moment or torque or work, whatever. A Newton meter. So when you notice that newtons are being applied, and so let's write it out as meters as part of this right here. We'll use meters, so we'll just divide by 1,000. All right. So we're writing out first off this force right here, and that force causes, if you notice, it's going to go, that 400 is going to try to make a clockwise rotation. That arrow doesn't belong on the diagram, but it's just to show you the thing. So writing that out is negative 400 times 0.160, which is the millimeters turned into meters. Now we proceed on to the other force that's applied. That's 692. If we would extend this guy right here, we would see that this distance right here, that 200 millimeters, this is the line, this is the distance that's perpendicular of a line perpendicular to the line of action right here. It's often the students get these confused, and it's a big distinction. We want to make it for sure. So that's 600. By the way, that 692 is also trying to go clockwise, and that's also students very much struggle with that. So you have to just try to envision that the thing is moving clockwise, right? That force is going in the clockwise direction. So 692.8 and times 0.2. and turning into meters, and then also apply the reaction, which is MB, and that equals to 0. If we do that, MB, we end up finding is 202.6 Newton meters, and right here. So this is the reaction right here. Now remember, in the sample problem, this direction will be opposite, because what they're trying to do is demonstrate what would be an equivalent moment, right? Determine the moment of the force about B. Like, what kind of moment does this force cause at B, right? As opposed to the one that is, well, opposed to it, which is the reaction. Now, the other way to approach this problem could have been, we could have just left this force, this 800 newtons here, but now taken a line of action for it that went down like this right here. And we could have used geometry to find what this distance is, right? And it would be perpendicular to here, right? We would draw all the same things onto it, in terms of its reactions. We would put all that on there, and we'd end up with the same value. MB would be onto there, okay? So I think I fully did, but it's a little bit more work, right? Because now we have to, and if we were to take a look at this thing right here, actually, we would find, I believe that right here, and right here, like this is 60 degrees right here. Playing around a little bit with the geometry right here, I think we would find that this is 60 degrees. Is that right? Because this right here would be 60 degrees right here. And so, no, I'd be wrong here. Okay, it's just that I drew it wrong, right? So, yeah, no, actually, I think so. It gets a little bit more complicated. So it's actually breaking it down into components. Whoops, I didn't mean to erase that. Breaking down to components, I find, is often a way to bypass some ugly geometry and trying to just find this right here. It's a lot easier sometimes to do it this way. So this is, be sure to look at what the sample problem, make sure that you realize, I wrote down here, make sure that you realize that this distance, this D right here, is not the distance between here and here, right? Because this is not perpendicular to the force, right? It's actually a distance like this right here. That's the actual distance because of this thing, right? So you got to be careful not to get fooled by the look of the problem. You want to be very, very careful. Sometimes it's best to make a scale drawing, and sometimes even to exaggerate the scale of the drawing to show that these two things right here won't just so that you don't get fooled by like that little trap, right? Sort of a trick problem where you might fall in and be very tempted to take a shortcut. So that's the sample problem.